This is the schematic diagram of a common emitter transistor amplifier. It might be either a low-frequency amplifier or a tuned high-frequency amplifier. The actual frequency is established by the resonant circuits, but the amplifier cannot function efficiently above the effective frequency limit of the transistor used. This film shows why. In a junction transistor, the emitter, with forward voltage, injects carriers, holes in this case, into the base. Then the holes travel to the reverse biased collector, where they become the collector current. In the P-type emitter, the majority carriers are holes. When current flows, new holes appear at the positive biased emitter terminal. In reality, they appear in large numbers, but we show only one at a time here so that you can see the action more clearly. The new holes repel the holes already present, so that other holes near the junction are immediately pushed over into the base. The signal is transferred through the emitter instantaneously. The signal also passes through the collector instantaneously. However, in the base, the signal is delayed. The holes are minority carriers here, so they must move individually, propelled only by their own thermal agitation. Each hole from the emitter must travel all the way across the base before it has any effect on the collector current. This delay in the base is called transit time. When an AC input is applied to the emitter, the number of holes injected into the base varies with the changing emitter voltage. Surges of holes travel through the base to become positive peaks of the collector current. Let's use meters to show the emitter current and the collector current. Although varying numbers of holes are constantly injected into the base, let's omit most of them so we can see what happens more easily. Due to the transit time, the collector current is slightly delayed. It lags a little behind the emitter current. This phase lag is very small at low frequencies, but the transit time is nearly the same regardless of the frequency in a given transistor. So, as the frequency is increased, the lag becomes a larger and larger proportion of each cycle's duration. This is one effect that transit time has on high frequencies. It's not very serious because we can correct for the effect of the phase lag, if necessary, by suitable circuit design. Transit time also causes a loss of gain, which becomes more serious as the frequency is increased. When a positive peak enters the base, many holes cross the junction together. In the base, only thermal agitation keeps them moving. Since they move erratically as they wander through the base, the holes tend to spread out on the way through. By the time they arrive at the collector, they may be distributed over quite a bit of the base thickness. Since there are fewer holes where the peak should be, we have less peak current than we had at the emitter junction. Both current gain and power gain are reduced. At very high frequencies, the holes spread out so much in the base, and the intervals between peaks are so short, that there is no variation of hole flow left when they reach the collector. In other words, all gain is lost in the base, and the transistor will no longer amplify. In practice, the upper frequency limit is the frequency at which half the power gain remains. At this frequency, the current gain is about 7/10 of the low frequency current gain, alpha. This is called the alpha cutoff frequency. It is one of the characteristic values specified for each type of transistor. The thinner the transistor's base, the higher the frequency it can amplify, because the current carrying particles do not remain in the base long enough to spread out excessively. Even with the thinnest possible base, however, the transistor still has frequency limitations. Depending on how the transistor is made, at some frequency, 10 megacycles in a typical case, the collector junction capacitance begins to present problems. This capacitance results from the behavior of the majority carriers, holes in the collector, and electrons in the base. The reversed bias draws all holes and all electrons away from the collector junction. This leaves a vacant region at the junction, a region of insulation that acts as a dielectric between the two adjacent layers of conductive material. It's equivalent to a capacitor connected between the base and the collector. The capacitance is very small. At low frequencies, its capacitive reactance is large and has no effect. However, the reactance decreases as the frequency goes up. At very high frequencies, the capacitance acts as a short circuit, and there is no gain left. The capacitance is actually distributed all along the collector junction. When AC flows, the capacitance is continually charged and discharged. Since the capacitance, in effect, bypasses the junction, it can be charged by the collector's voltage source. This charging current flows through the base, a narrow, crowded path that has resistance. The base resistance consumes power that would otherwise be available as output. And the higher the frequency, the greater this power loss becomes. We can counteract the effect of this capacitance by making it part of a tuned output circuit. But it will still be there, drawing charging current through the base resistance and causing an unavoidable power loss. We can reduce the collector capacitance by increasing the collector bias voltage. This draws the majority carriers farther away from the collector junction, making the vacant dielectric region thicker and the capacitance less. This also makes the base thinner, and the high frequency performance is improved for that reason too. However, the overall improvement is less than you might expect, because in making the base thinner, we have increased its resistance. The high frequency gain is limited by the power loss due to charging current. Although the base thickness, the collector capacitance, and the base resistance all affect the transistor's frequency gain, they do not by any means make the transistor useless at high frequencies. The transistor's small size and low power consumption more than offset its high frequency disadvantages in many applications. For example, this three-stage circuit using surface barrier transistors is a direct coupled video amplifier. It is an efficient amplifier of frequencies up to 10 megacycles. Yet it consumes very little power and is not much bigger than the end of your thumb. This is a transistor oscillator. The frequency it generates depends on the resonant frequency of its tuned circuit. Naturally, the transistor used must have suitable frequency characteristics. But a given transistor can be made to oscillate at much higher frequencies than it will amplify usefully. All oscillators include three essential elements. First, an amplifier. Second, a resonator or tuned circuit to fix the generated frequency. And third, a feedback arrangement to return some of the output energy to serve as the amplifier's input. In order to maintain oscillation and supply an output, the amplifier must have enough gain to supply its own input, replace all circuit losses, and have sufficient energy left over to deliver adequate output. This is a very simple oscillator. Transistors will work just as well in a great variety of other oscillator circuits, including most of those in which vacuum tubes are employed.